This week we start off by looking at a device called a dynamometer, and here's one pictured over here. Basically the device is used to measure the power output of, in this case, an internal combustion engine. What you see over here in the distance is an internal combustion engine out of a motor car that's being tested, and it's connected by a drive shaft. You can't quite see it, but the drive shaft connects to this device, the dynamometer over here. Here's a bearing and here's a bearing, and obviously that all rotates because it's connected to the drive shaft. And then inside this housing, you obviously can't see it, but there's an impeller, which is basically a series of, let's call them blades, and they are running within a liquid. In this case it's water, and if there's no water in the housing, then the shaft would be free to rotate, and there would be no reason for this casing to be rotated, to be dragged around with the water and the impeller. But if you put water into that space, this arm suddenly gets pushed downwards because the whole casing is trying to go along with the rotating impeller inside. And in fact, the more water you put in, the more of that effect there will be. And that way you can control how much torque you take from the engine. And ultimately, if you know the value of force in this load cell over here and you multiply it by the radius from here to the center line of the shaft, you would have the torque. Now whilst it's running, that water is obviously going to get warm and ultimately boil eventually, so they circulate the water through a cooling device which is outside of this picture, and that way control the energy dissipation from the engine, because ultimately the engine is producing power. Remember, that's joules per second, so those joules, that energy has to go somewhere. You can't destroy it, as we know. All that you can do is transfer it to the water, and that heat would be taken away and dissipated elsewhere through an appropriate radiator, cooling tower, etc. Now remember, the purpose of the device is to measure the power output of the engine, and we know that power is torque times rotational speed. So if we know what the torque is, and remember the torque was whatever force was in this load cell multiplied by the perpendicular distance to the axis of rotation would give you the torque. If you multiply that by rotational speed, you can get the power of the engine. So now would be a good time to add these two formulae to your summary sheet, and here it is in the most basic form. Power is torque times rotational speed. Here's the units defined: power measured in watts obviously, or joules per second. Omega is our angular speed in radians per second, or if you prefer to work in revs per minute, it would be power is 2 pi nt over 60, where T is torque measured in Newton meters. And now angular speed is not in radians per second like it was in this formula, it is now in revs per minute. At this point, I'd suggest you go and look at these various clips, which give you a number of different examples of dynamometers in action, which will better explain what we've just been through. You'll note that in some of those clips, the dynamometers are of the rolling road type, where they are testing the output of a motor car, and instead of removing the engine and connecting it to a dynamometer like in the first picture that I showed you, they instead put the drive wheels onto two submerged rollers, which are then rotated by the wheels of the vehicle, and then those submerged rollers, you probably can't see it, but underground or elsewhere, they are connected to a dynamometer of a similar type to what we spoke of earlier. So here's the simplest type of example. We are told that a dynamometer with an arm of effective radius 600 millimeters, remember what that was? That was the distance from the axis of rotation of the shaft to where the load cell was applied. That is 600 millimeters. In this example, it registers a load cell force of 167 newtons, but the dynamometer is turning at 4,800 revs per minute. What is the power of the engine driving the dynamometer? Well, torque, as we said, is force times radius. So there's the force measured in the load cell. There's the radius, obviously in meters. So we have 100.2 Newton meters. Now we bring in speed of rotation, and we know that P is 2 pi nt over 60. 2 pi times 4,800 revs per minute times the torque over 60, gives us 50.366 kilowatts. This next one is not a dynamometer as such, but it operates in exactly the same fashion. We are told a shaft runs in two bearings. Whilst the shaft is running at 1440 revs per minute, a bearing drag of 2 Newton meters. Now that would be some problem with the bearing, poor lubrication, or a bearing that's starting to fail. The point is there is bearing drag, or the bearing outer housing is being carried along with the rotating shaft to the extent of 2 Newton meters. This is assumed to be caused by bearing friction. So as I said, a problem with the bearing. What heat will be dissipated by the bearing during 1 hour of operation? Now that bearing would get warm because that energy has to go somewhere. And in this case, we don't have water like in the dynamometer taking the energy and getting rid of it somewhere else. It is staying with the bearing housing, and that bearing is going to get warm. How much heat are we talking about in 1 hour of operation? Well, remember there was 2 Newton meters of bearing drag, so that's our torque. It was all happening at 1440 revs per minute. So we are talking about 301.59 watts, or as we know, that is the same as joules per second. So in 1 hour, which is 3,600 seconds, the heat that you're dealing with is that times that, which would give you 1085 kilojoules of heat. Now this very method is used in industrial applications for maintenance of machinery. If there is indeed a bearing that is giving trouble, this heat you can detect using thermal imaging devices. So relatively quickly you could walk around a factory between the machinery with a thermal imaging camera and focus it on the various bearings of the different devices, and if you find one that is warmer than the ambient temperature significantly, you could suspect that there's a problem with the bearing, and then you could institute a maintenance plan to solve that problem. Now we move on to a device called a Pelton Wheel, and I'd suggest you start by looking at this very good clip over here. But basically what you're going to learn from that clip is the fact that this Pelton Wheel extracts energy from the impulse of moving water, okay, as opposed to various other types of water-driven device which are less efficient. This one is particularly efficient, and it is widely used whenever you need to extract energy from water, flowing water. So where would you use a Pelton Wheel? That would be an obvious question. Well, if you have the need to generate electricity, maybe for your own needs or the needs of your industry or whatever, and you happen to have a source of water at an elevation above where you are, in other words, the water has head, and you are able to pipe it down to where you are, and ultimately rotate a Pelton Wheel, which in turn drives a generator, you can produce electricity. That would be first prize. And there are parts of the world where such geographical conditions exist. In South Africa there are a few places, particularly rivers with a high fall. You can find those along the Transkei coast. There are quite a few small rivers that would be ideal for such applications, some farming applications. And then on a larger scale, the energy utility Eskom also uses devices similar to this, but they use it for a different reason, and that is energy storage. What they do is, when electricity is in oversupply, certain times of the day when the power stations are producing more electricity than the grid requires, then they will use surplus energy to pump water to a high elevation, a dam that is high up on a hill, and then later in the day when the electricity is in demand, they would then release that water back down the hill through the Pelton Wheel and make electricity and put it back into the grid. Obviously there's a loss in all of this, probably up to 20% is lost, but it still suits their needs to store the energy and then reuse it later when they need it again. So there are a number of those schemes in South Africa. Now if you are using it for what we just said, for energy storage, what you are basically doing is you are storing mass at an elevation. And remember that that is what's called potential energy. So you could just as well lift a large concrete block of mass M through a vertical height h using a winch and a cable, and then you could then run that weight downwards again and rotate the winch in reverse and drive a generator and make electricity. It would be exactly the same as what you're trying to do with the water. In this case, we have the water, which is either in this dam or this dam, and it is lifted from this dam to the higher one and then allowed to flow back down through the turbine and generate electricity. So that would be an identical situation, either a mass that is physically raised or water that is physically raised. In both cases, we would be dealing with potential energy of a certain mass. Now, as we well know, potential energy is mass times g, which is weight, times height. That would be the amount of potential energy that you have stored, and we could rewrite that as weight times height. Now, if we apply that to a liquid, for liquid flowing in the pipe, in this case this one here, at Q, remember that was how we measured discharge in cubic meters per second, with specific weight omega. Now remember, specific weight you learnt in previous chapters was measured in newtons per cubic meter. That was the specific weight, which was the weight in newtons per a specific volume, in this case a cubic meter. Okay, so the weight per second would therefore be omega times Q. The newtons per cubic meter multiplied by the cubic meters per second would leave you with weight per second. So the energy per second would be weight times height, and we've just figured out that the weight would be omega Q times the height that we are dealing with, would boil down to the fact that the power available is omega, specific weight, times discharge, times height. And that is called the hydraulic power. That is the amount of power available without any losses being considered, just by virtue of the fact that the water had been lifted from here to here and was now able to run back through height h. If we know how much is flowing, we know what the liquid is, what its specific weight is, and importantly how high it is. If we multiply those three numbers together, we get the potential power that we can get out of the system. Obviously you can never get more than this. That is the physical limit. Alternatively, you can look at it a different way. If you simply look at it as plain potential energy, if liquid is raised, it gains potential energy, which we know is mgh. Now the mass would be density times volume. So we would have density times volume times g times h. And if we work per second, we would have density times q. Remember, q is measured in cubic meters per second. But rho times g we know is specific weight. So we are back to specific weight times q times h. And because it is energy per second, it is in fact power. So the power is specific weight QH, as we learned before. So the same outcome. Now, we often speak about the energy problems of our country and the load shedding that we have from time to time. And you'll hear and see many people that try and go off grid and try and make their own electricity, which is all great. And they might have solar panels on their roof and they generate electricity during the day, no problem at all. But what do they do to get through the night when there's no sun shining on those solar panels? Well, most people buy batteries and they charge the batteries. These are lithium-ion batteries you see in this picture. And then they feed that current into an inverter, which then powers the house during the night. Now, that's all fine and well, but it's a very expensive way. Is there an alternative to storing the energy in another way? Well, how about using a solar pump, a solar-powered pump, to pump water from a dam during the day when the sun's shining and get it into a dam that is situated at higher elevation on the top of a hill perhaps, and then at night to run that water back down through the device we've just learnt about, a Pelton Wheel, and then power your household during the night. Well, that sounds like a fantastic idea. Let's do some calculations via this problem to see how feasible that is. So let's read through the problem as it's given to us. A small pumped storage system is depicted. That's what this would then be. A Pelton wheel is used to generate electricity at night by allowing the water to flow from the top storage dam, that's this one, to the Pelton wheel, that's down here, after which the water enters the lower dam. So its energy is extracted via the Pelton wheel, which then drives a generator, which is not shown, and the water would now be devoid of its energy and it would just simply fall into the dam, which is right there. During the day, the water is pumped by a solar pump, not shown, from the bottom tank back to the top dam. We discussed that already. Assuming the average head is 80 meters, as shown, and that the Pelton Wheel generator combination operates at 85% efficiency. So remember, nothing is ever 100% efficient. So they're saying that 85% of the energy is extracted as electricity. Now, how many kilowatt hours of energy can be generated from 100,000 liters of water in 3 hours? So 100,000 liters of water will go from this dam to this dam in a period of 3 hours. During that time, how many kilowatt hours of energy will be generated? Well, let's start by looking at the flow, the discharge. If we have 100,000 liters, which is 100 cubic meters, by the way, and it is passing through the pipe in 3 hours, what would be our discharge? Well, discharge is measured in cubic meters per second, remember. So we're dealing with 100 cubic meters in this many seconds, which would be 3 hours times 3,600. Remember, there are 3,600 seconds in 1 hour. So we are dealing with 9.259 times 10 to the minus 3 cubic meters per second. Now, what's not written in the question in the words is on the sketch here, and that is the fact that there is friction in the pipeline as well. The pipeline is 120 meters long. It has a diameter of 75 millimeters, and here we are told that the friction coefficient is 0.007. So we had better take into account the head lost to friction, which we've done in previous work, but let's see how we can work that out. If we look at the friction formula, we need to know the velocity of flow. So let's see if we can work that out. Remember that Q equals VA. So V is Q over A. Q is our discharge, there we have it, over the area, the cross-sectional area of the pipe, pi over 4d squared, meaning that the average velocity in the pipe is just over 2 meters per second. And our friction formula, the Darcy formula, says head loss to friction is 4 times the friction coefficient times the pipe length times the mean velocity squared over 2 dg, diameter times g. So it's 4 f l v squared over 2 dg. It means that roughly 10 meters of head is lost to friction. So of that precious 80 meters, 10 is going to be lost to friction. Remember, the only way to minimize that would be to use a bigger diameter pipe and drop the velocity of flow. But there'd obviously be an expense involved. So the effective head is 70 meters. So our potential energy of the water is mgh, as we know. So we have a mass of 100,000 kilograms of water times 9.81 times the available effective head of 70 meters. We are dealing with 68.67 megajoules of energy. And remember, only 85% of that is available to us because of the losses in the machinery at the bottom. So that is how much is left for us to use. And if we're going to use it in 3 hours, the rate of energy generation would be the total divided by the time involved, which is 3 hours, each hour being 3,600 seconds. Meaning that we are dealing with 5404 joules per second, which is 5.4 kilowatts. And kilowatt hours, remember, are the number of kilowatts that you are dealing with multiplied by the number of hours you do it for. So that would come out to 16.2 kilowatt hours of energy. So in summary, this pumped hydro system with its 100,000 liters of water at 80 meters would only produce 16.2 kilowatt hours of energy storage, which might or might not be enough for your application. Now here's a little practical example of a real Pelton wheel, and there is the data plate on the Pelton wheel. Now if we zoom in and have a look there, this manufacturer is claiming that at a 15-meter head, that's what that says there, with a discharge of 25 liters per second, they are saying that the device can produce 2.8 kilowatts. So let's see what that works out to as an efficiency. we must calculate the manufacturer's claimed efficiency of the Pelton wheel. Oh, and the speed of rotation was 766 revs per minute. Now, efficiency in this case is actual power derived from the unit divided by the hydraulic power that it used. So we could put it a different way. We could say that actual power, which they're claiming is 2.8 kilowatts, is equal to this multiplied by that. So the 2.8 kilowatts is equal to the hydraulic power, there it is there, multiplied by the efficiency. So if we solve for the efficiency, it turns out that this machine, they are claiming a 76% efficiency. So it produces 76% of the hydraulic power as a shaft output from this particular Pelton wheel. Now we move on to a different type of hydro device, namely a pump. And this is probably the most common type of pump you're likely to encounter. We have an electric motor driving through a shaft, which you can't see here, the actual centrifugal pump, which is this piece over here. And this pump would draw water in through a pipe connected to this flange, which is obviously off at the moment, and it would essentially fling the water outwards until it left through this passage over here, and there'd be an exit pipe, an outlet pipe attached to this flange, and the water would then go to wherever you need to take it. So I would strongly recommend you take a look at this clip over here, which is quite good at explaining the workings of a typical centrifugal pump. Now, before we go any further, let's sort out this one matter of the maximum suction head that is possible with any pump. Now, the pressure differential causing water to enter and rise up the suction pipe of a pump, that's this side over here, this is the suction pipe, is caused by the difference between atmospheric pressure and the reduced pressure caused by the suction device, the pump in this case. So the pump is causing low pressure here, and it is allowing the water to rise up and enter into the pump at that point. But now here's the crux. The lowest pressure attainable is 0, hence the maximum theoretical suction head possible is 10.32 meters at sea level. Okay, so in practice you can never get to 10.32 meters, regardless of how good your pump is or how much power you're putting into it. The point is, you cannot have the pump more than 10.32 meters above the surface of the water from where you are drawing. In reality, you can never actually get close to 10.32. It should always be much less. But the bottom line is the pump should always be mounted as low as possible to prevent other issues such as cavitation and the need for priming. So in other words, if this was a river, there's the surface of the water, and here's a mountain, for example, over here, and you want to get the water from the river to the top of this mountain, and you want to install a pump. To go and install the pump up here and ask it to suck water from the river far below and deliver it to where you want to go might sound feasible, but it's not, because this pump has to be way down within 10.32 meters of the river surface, or preferably right down as close to the water as possible, because otherwise if you mount it anywhere higher up, it simply won't pump regardless how much power you put in, because the pressure differential will just simply be not enough to get the water into the suction side of the pump. Let's look at why that is. This very example that I drew out now, basically the water that rises up the suction pipe to the pump is done so by the fact that we have zero pressure inside here, zero absolute pressure, and we have atmospheric pressure acting down on the surface of the water, and the best we can get in terms of this height is atmospheric pressure times specific weight of the water times h, which we're solving for, and we find out that 10.32 meters is the absolute maximum suction head possible, and that is for our atmospheric pressure on planet Earth. Now when we deal with pumps and installation of pumps and selection of pumps, etc., we will more than likely come across pump curves. Now here's a pump curve, a typical pump curve for a set of centrifugal pumps. Let's focus on the BAV 150 pump, whose pump curve is this line over here. Okay, now on the graph we have head on the vertical axis and we have flow on the horizontal axis, and they give it in various units for your convenience. So we need to look at this example. It says, for example, at 100 liters per minute, the BAV 150 pump can produce 3.5 meters of head. Let's have a look how that works. So let's find 100 liters per minute. Let's find the appropriate scale, liters per minute at 100. Looks like it's over here. And we go up until we reach the pump curve, and then we go across and we find 3.5 meters of head. So that's just a fact of this particular pump. They've done some performance testing on it, and they found at various heads you get various flow rates. Conversely, we could say at 2 meters of head, which is here, we could go across until we reach the pump curve. We could go down and see, the flow rate's going to be 8.4 cubic meters per hour. Have a look where that is, 8.4 cubic meters per hour. So for each and every head you can find a corresponding flow rate, and vice versa for that particular pump, and that is how you would select the pump for your particular application. 2 meters, 8.4 cubic meters per hour. Now earlier we looked at efficiency when it came to a Pelton wheel, and we took the lesser number and we divided it by the potential number, the possible number, and we got a ratio between 0 and 1, which we called efficiency. In the same way, we can apply pump or efficiency to a pump, and this is the actual hydraulic power achieved divided by the input power to the pump. So it's working in the opposite way to the Pelton wheel. We are supplying power to the pump and we are achieving hydraulic power from it. Hydraulic power is the rate of work done on the water. Because the water is raised through a vertical height by the pump, it gains potential energy. So the pump, we are driving the pump with a prime mover, an electric motor or a petrol engine or whatever, and we are getting out of it hydraulic power. Now remember, hydraulic power was omega or WQH, and we can then work out the pump efficiency if we know those two values. Let's look at it by example. A pump delivers 110 cubic meters per hour of water to a point 50 meters above the suction point. The input power to the pump from the motor shaft is 20 kilowatts. What is the efficiency of the pump? Well, let's look at the hydraulic power that we achieve. Specific weight, QH. Specific weight, 9810 newtons per cubic meter. Discharge 110 cubic meters per hour, so we must divide that by 3600 to get it per second, times the 50 meters that we raise the water through. So our hydraulic power is 14.98 kilowatts, but remember we put 20 kilowatts into this device from the electric motor, and we were only getting 14.98 kilowatts of hydraulic power out of it, which means it was running at 75% efficiency. Now, moments ago we looked at a pump curve that simply had head against discharge, and it was a single curve, but we can get a more elaborate pump curve if we add another scale on this side, which is a dual scale of power and efficiency. And now we can add further curves to the very same graph that we saw earlier. This was the pump curve that we were familiar with earlier, the blue one. Now, if we look at efficiency, which we just worked out moments ago, and we plot that at the various points of flow rate, and we look at the efficiency on this scale over here, we can find that the efficiency is not always the same. In fact, it definitely peaks at a certain point and then starts to drop off again. So if we did the calculation that we did earlier up here, we did it for each point on the curve of the pump, in other words at each flow rate versus head situation, we would have various efficiencies, and if we were to plot them, we would find a spot where the efficiency was at the greatest. Now, in the perfect world, we would like to run our pump always at that spot there so as to achieve the most output for the amount of input we are giving the pump. In other words, at the most efficient point. Now in reality we can seldom run at exactly that sweet spot over there, so we would have a range either side that we would like to operate in, and in this particular case they're saying the recommended operating range would be in this zone over here. So the long and the short of it is, if you were to order a pump and you were to order the pump and run it, let's say at 400 cubic meters per second and run it, per day in this case, the 400 value, you would be sitting over here, which would work. We would be achieving a head of 12 and a bit meters and everything would be fine, but we would not be at the optimal point in terms of efficiency. Yes, the pump would work, but it would not be a well selected pump because we would be not in our most efficient range. So look at this graph and the various axes and see if you can make sense of how it all works out. Let's start by using the blue and the green curves only and calculate the shaft power required to pump 50 cubic meters per hour with this pump. Now 50 cubic meters per hour, we need to get it to days because that's what our axis units are. So we multiply by 24 and we get 1200 cubic meters per day. So now we read off the blue curve and we find that we can do 6.5 meters of head. And then we read off the green curve and we find that the efficiency will be 70%. Let's go and look that. So we take 1200, we go up to the blue curve and we go across and we find our 6.5 meters of head. And we also note that the efficiency is 70%. Okay, so if the efficiency is 70% and our output is the hydraulic power of a specific weight QH, we can solve for the shaft power that we should be requiring, and that comes out to 1.265 kilowatts. Now this graph has the power expressed in horsepower, and remember that the conversion is 0.745 between kilowatts and horsepower. So you divide 1.265 by 0.745, which makes the number bigger, which is correct, comes to 1.698 horsepower. Let's call it 1.7 horsepower. So let's go back to the graph. Now we're looking at the red graph, which is power expressed as horsepower, and we go here and we go across and we see it looks like 1.7 horsepower. So we could have just simply read it off the graph, or as you can see, the calculations can be used. If you are lacking, for example, the power curve, you could work it out, and vice versa. This particular graph with all these various curves on it just does some of the calculations for you. But it's important for you to know where the calculations come from. The final type of pump we're going to look at is a multi-stage submersible type of pump. And basically what that is, it's a number of centrifugal pumps stacked one on top of the other, and the outlet from one pump becomes the inlet of the next pump, and so on. And that way the pressure output of what's essentially a centrifugal pump is greatly enhanced. A centrifugal pump typically is not a high pressure pump, but if you do it this way and make it multi-stage, you can obtain significant pressure from the very simple centrifugal type pump. And the submersible type is often used in a borehole environment, so it's a long, small diameter, long, narrow type pump. And I would strongly recommend that you go and look at a YouTube clip such as the one over here to get an idea of the workings of a submersible multi-stage pump. And the next problem is going to focus on one such device. In this final example, an actual product out there made by Grundfos is used as the basis of the problem. In this case it's a 10-stage SP8A-10 Grundfos pump. It's a submersible centrifugal pump, is used to pump water from a river to a dam situated 50 meters higher than the river. So the head must be 50 meters there. The pump is powered by a solar source, hence assume that it only operates for 6 hours a day. So when there's sun, the pump runs, and when there isn't sun, the pump is off. At night, all the water in the dam is allowed to flow back to a Pelton Wheel situated at the level of the river in 2 hours. So whatever went up during the day comes back in 2 hours. The 50mm diameter pipeline from the dam to the Pelton wheel is 75 meters in length and has a friction coefficient of 0.007. Neglect friction losses in the pipeline from the pump to the dam. So you don't have to worry about friction on the way up, but it looks like you do need to worry about it on the way down. Question 1. What quantity of water in litres will be in the top dam at sunset? And then use that answer to calculate the hydraulic power attained and hence the pump efficiency. And then finally, assuming that the Pelton wheel generator combination has an overall efficiency of 88%, how many kilowatt hours of electricity can be expected to be generated per night? Okay, so spend some time on this one. Look at that link and the data sheet on that pump. You're going to need that. And here is another resource for you, which is the same curve, SP8A-10. That is the same as that curve there. And here's the power, which is expressed on both graphs. So you can use either resource to work that out. So make a good attempt at that. Stop the video now and have a go at that one. So the SP8A-10 at 50 meters head can do 4 cubic meters per hour. For 6 hours a day, that is 24 cubic meters per day, which is 24,000 liters. Next is the hydraulic power. Specific weight, discharge head, multiplied together gives us the hydraulic power. Specific weight of water, 9810 newtons per cubic meter. Discharge through the pump is 4 cubic meters per hour, so that is 4 cubic meters divided by 3,600 to get it to seconds, cubic meters per second, times the 50 meters head that it is pumping through. That is 545 watts. Right, how much power is the pump using? Well, we've got 50 meters head, and if we go down, remember we were doing 4 cubic meters per hour, so here's our line. On the power curve, it looks like 0.1, 0.12, looks like 0.11 kilowatts, but that is per stage, and remember it's a 10-stage pump. So 0.11 kilowatts per stage times the 10 stages. Remember there's 10 centrifugal pumps effectively packed on top of each other. The total is 1.1 kilowatts or 1100 watts. How efficient is our pump? Well, it's giving us 545 watts of pumping power, hydraulic power, yet it's using 1100 watts of electricity, so it is 49.5% efficient. Now onto the Pelton wheel. At night, those 24 cubic meters flow back in 2 hours, so that would be 3.33 times 10 to the minus 3 cubic meters per second flow rate through the Pelton wheel. Velocity of flow in the pipeline that supplies the Pelton wheel, remembering it's a 50mm pipeline, Q is VA or V is Q over A. So there's our discharge. There is the pipe area, pi over 4d squared. It means that the flow velocity is 1.7 meters per second average in that pipe. Darcy formula, 4FL V squared over 2dg, means that 6.187 meters of head is lost. So of the 50 meters that we had in total, we lose 6.187 meters, so we're only left with 43.8 meters effective head. So what power can we get out of the Pelton wheel? Well, hydraulically, we have 9810, which is specific weight of water, times the discharge, times the 43.8 meters effective head. It means that the maximum power, the hydraulic power, would be 1.432 kilowatts. And remember, we're working for 2 hours. We multiply by 2 to get kilowatt hours, but we have to reduce the number because of the inefficiencies of the Pelton wheel generator combination at 88%. So we multiply by 0.88. So all we get out of the system ultimately is 2.52 kilowatt